Here we're going to look at a rate of change problem that's not a position, velocity, acceleration problem. What we've got described here is a colony of bacteria that's growing according to this formula, which represents millions of bacteria where t is measured in hours. So, for example, n of 0, which is the first question they ask, what you get is when you plug a 0 into that, you just get 10 over 2 or 5. So it starts out with 5 million bacteria, and then this formula tells me the subsequent population or subsequent number of bacteria in that colony as time goes forward. So we got some questions we want to ask, and we'll kind of interpret some things. First one is n prime. That is going to require me to do a quotient rule. So it's going to be the derivative of the top. Let me write this one out. Derivative of the top, which is 10 plus 20t, times the bottom, 2 plus t, minus the derivative of the bottom, which is 2 plus t, times the top, which is 10 plus 20t. And then that's all divided by the bottom squared, so 2 plus t squared. And so if I do these derivatives, I'm going to get a 20 times 2 plus t minus 1 times 10 plus 20t, and that's all divided by 2 plus t squared. If I were to multiply these out, I'm going to get a 40 here, and then over here I'm going to get a minus 40 plus 20t, sorry, trying to think ahead, minus 10, and then this is going to be a minus 20t. So the t's are going to go away. I'll have 40 minus 10, that's going to be 30. So my derivative of prime, that looks like a double prime, but it's really just a single prime, is 30 over 2 plus t squared. And this would be in number of bacteria, millions of bacteria per hour. That's the units on this function. So put in a t, for example, put in t equals 0, and you get 30 over 4, which tells you the initial growth rate of how fast this thing was growing, how many bacteria per hour are being added at that point. So this keeps track of how many bacteria are being added per hour. Second derivative can be a little bit messy. Let's go ahead and calculate that. I'm going to have to take a quotient rule again, so it's the derivative of the top, which is the derivative of 30. That's going to be 0, but this next part's the messier part. Then I got to do the derivative of the bottom, t plus 2 squared, times the top, and then that's all divided by the bottom squared, 2 plus t squared squared. Okay, so like I said, that's 0 because the derivative of that constant 0. This derivative I'm going to have to do as a product rule, so I'll just do it up here. It's going to be the derivative of the first. So I'm writing this as t plus 2 times t plus 2. And so it's going to be the derivative of the first t plus 2 times the second t plus 2 plus the derivative of the second t plus 2, which looks just like the first one, but anyway, times the second t plus 2. So that's our product rule. It's the way I have to do that at this point. Well, this is going to be 1 times t plus 2, and so is the other one. And I'll just leave it as 2 t plus 2 without multiplying it all out, because that's going to cancel with the denominator here. So that's what this numerator is, 2 t plus 2 over, somewhere I switched to 2 plus t and t plus 2, but anyway, sorry about that. There's the same thing, right? Down here in the bottom, I've got t plus 2 to the 4th. I'll multiply those exponents, and I can cancel one of the t plus 2's, and this was negative, so I better be sure to keep that in there. And there was a 30, so I better keep that in there too. Anyway, I end up with negative 60 over t plus 2 to the 3rd power. So that's my second derivative. Second derivative is negative 60 over t plus 2 to the 30th power, or 2 plus t if you like. And this is in number of bacteria per hour. So that's the change in the change. I mean, in other words, it's telling me how that growth is changing. And so a lot of times they'll say hour squared, but it is really number of bacteria per hour. So that's your second derivative. That was what I was asked to find. So let's see what we want to do with these. Okay, so now it asks, when are the derivative and the second derivative positive, negative, or zero? Sort of what we did with the velocity, trying to figure out, when it's moving forward, backwards, or whatever. But when I look at this, that numerator is just 30, so that's always positive. And the denominator is a square, so it's also always positive. So what I can say for that's number 3. For number 3, the derivative is positive for all t, which means I have positive growth. This thing is growing. The culture of bacteria, this colony of bacteria, is growing from the start. It starts at 5 million. It's going to keep growing. That's what this derivative is saying. So it's going to always be bigger than 5 million. Now let's look at the second derivative, find its sign. Well, looking at this one, I don't know where that 30 came from in here. Erase that. That should have just been 3, and it won't let me erase it because it's just trying to point out that I screwed it up, I guess. All right, there it is. That's supposed to just be 3. All right, I canceled it and then didn't write it down right. So when I look at this one, so I'm only looking for t's greater than or equal 0. So if I'm doing that, this denominator is going to be positive because I'm only putting positive numbers in there, and this numerator is going to be negative. And so what that tells me is my second derivative for the values of t that I'm using, second derivative is always going to be negative, and that's for the t's that I'm using. And so what is that saying? That's saying that my growth rate is declining. So this is my growth rate, and it's declining because this is negative. The second derivative means it's getting, the change is getting less and less. So the idea is that, yeah, it's growing from the time we starts at 5 million. It is growing, but it's growing at a slower and slower rate. In terms of tangent lines, that means your tangent lines, if you're thinking of a curve, the tangent lines are getting less and less steep as you go forward. So thinking of it kind of geometrically. And so that's how I'm interpreting the results on what's happening there. So it is always growing, but it's growing at a slower and slower rate, which sort of makes sense because, bacteria, they don't have unlimited capacity to grow, especially if you have them trapped on a piece of bread or something. They can't just take over the whole world. And so they will finally fill up the piece of bread or whatever they're in a culture, and then that's a natural limitation. And so that's what this is showing. It looks like it's being limited, and that's what this number 5 is actually going to show us. I'm going to take the limit. I'm going to have to do it up here. I won't see it. So right here, I'm going to do the limit as t goes to infinity of this function, 10 plus 20t over 2 plus t. Well, this one we can do. Remember, this is a rational function, so all I have to do is take these dominant terms of, this is the same as taking the limit as t goes to infinity of 20t over t, which cancel out the t's. You're going to get 20. So that says, in the long term, it's headed towards 20 million bacteria. That's the limiting value of this culture. So we can see that we said it's tailing off, less and less growth, and now we know where it's tailing off to. It's tailing off to 20 million. So they want us to provide a sketch. Well, putting all that together, I would do something like this. It starts out at 0, t equals 0. It starts out at 5 million, and then I didn't leave myself enough room to make it, we'll just say that's 20, even though it's not really 4 times that, but it's going to trail up here, and so it's got to grow in a nice smooth way. You can see that the tangent lines to this curve that I'm drawing would get less and less steep, which that's what the second derivative is telling me. Those tangent lines are going to get less and less steep. But they are positive tangent lines, meaning that the derivative is positive all the way through here. So geometrically, this is what the graph would look like on this bacteria culture, this bacteria colony that we have. It starts out at 5, and it will approach 20 million as time goes forward.